In last few lectures, we have discussed about the stability, how we can study the stability of the system. From now on, we'll be starting how we can design the controls for the nonlinear system. So our first control techniques, we are going to start the feedback linearization based control. So here, basically, if you have nonlinear system here, and we're gonna use some concept, which is basically feedback linearization concept, which help us to convert the system into linear form. And once you have the linear system, we can design the linear control techniques. And that actually going to help us to derive the nonlinear controls for the nonlinear system. So this is basically the concept behind the feedback linearization based control. So let me write some notes before we push to the examples. So here, the feedback linearization techniques, the feedback is a control technique or control method used to transform transform a nonlinear system into a linear one through a change of variables. And this allows the use of linear control technique to design controllers for nonlinear system. So this definition actually what we have explained here, though from the nonlinear system, we're going to use the feedback linearization technique, which help us to convert the nonlinear system into linear form. And for the linear form, we can design the linear control techniques, which indirectly will define the nonlinear control for the nonlinear system. So let's start with the motivational example, which will help us to understand this concept. Example. So how this technique works. Let's work on this. So let's consider we have a system, the following nonlinear system, which is defined by x double dot plus a sine x plus bx dot equal to cu. So here, if you notice here, um, this is the control here, this u we are going to design, and this u is going to control the state of the variable x here basically. So here our main motivation is design u to control x. So here basically, if you notice, the system is nonlinear. So we have to design the nonlinear control for this system, but since we are going to use this method, feedback relation technique, so our motivation is how we can convert this nonlinear system into linear form and how we can design the linear control. So here, as for the rule, what you have explained here, change of variables. So we are going to apply the change of variable for the system. So let's do it. Change of variables. So here we're defining x1 equal to x, and x1 dot equal to x dot, or we can define x2. So if you apply this variables to the nonlinear system, which is defined by equation 1, so we can write the equation 1 in state space form. We can write x1 dot equal to x2 and x2 dot equal to minus a sine x1 minus bx2 plus cu. And let us define this is equation 2. Now, this is the basically two first order ODs. So we have to design the control EU to control state x2. And if x2 is controlled, we can control x1 because x1 depend on x2, right? Now, let us choose u equal to for the first second equation x2 dot equation equal to a upon c sine x1 plus 1 upon c v. So here v we are considering is newly, we are defining some variable newly defined variable. So basically this v will help us to design the linear control. Now if you substitute this the expression of u in equation 2, so we can write, so let us define this is equation 3. Now substituting equation 3 in equation 2, we can write x1 dot equal to x2 as it is, but x2 dot yields to minus bx2 plus b. So now the interesting equation we have, this is equation, for example, 4. So this system is linear system. The system, if you notice here, this system is a linear system, right? There's no nonlinear terms in this equation. So in state space form, we can write equation 4 in state space form. We can write x1 dot, x2 dot, and we have matrix 0, 1, 0, and minus b. We have the state vector here, x1, x2, and we have the B matrix 0, 1, and B. So if you notice this equation 5, this is basically the system is represented in linear form and also state space form. So while the discussion of modern control, we had the state space model in linear form, and we can design V in such a that x1, x2 can be controlled. So here, since the system into linear form, we can apply the pole placement control technique or regulator problem, and we can design the expression for V, and this V can control the states x1 and x2. So here we can write, this is the linear system. We can design a linear control. What we have done already, what we have covered in modern control in the first half of this course. So now let us choose V as a state feedback control Kx, or we can write K1. There's two states, so we are going to have two control variable K2 and X1, X2. So we can define K1, X1 and K2, X2. And now if you substitute the expression of V in equation 5, equation 6, substituting equation 6 in equation 5, we are going to have x1 dot equal to x2 and x2 dot equal to minus bx2 minus k1 x1 minus k2 x2. So if you notice this equation actually in controlled form, actually in closed loop form, because V has been designed, this V has been designed using the variable x1, x2, which is coming from the sensors or from the output. So this is basically closed loop system. And if you write in state space form or in augmented system form, x1 dot, x2 dot, we have the 0, 1 minus k1 minus k2 plus b, and we have x1, x2. So this is basically a linear system, which is in closed loop form. And the way how can design K1, K2 already we have done multiple times while discussing our modern control. So K1, K2 we can design based on the desired dynamics, and we can find the expression for V. So this is how we can design the linear control for the linear system, which is defined by equation 4. Right. Now, we can write, if you notice here, we are now taking the linear system. So what about our original nonlinear system? So the control for the nonlinear system, we can write. So here, let me write here some notes. So here, K1 and K2 can be designed based on standard pole placement technique. So now the overall control we can design, the overall nonlinear control for the system defined by equation 1. Now our last part, how we can design the control for this nonlinear system. So here what you're going to do is we'll substitute in this equation the expression of V. So we'll get the overall nonlinear control, which is going to control the whole system. So now we can write E equal to, which is our U expression actually, we can write A by C sine x1 1 upon C B, or we can write A by C sine x1, and we can substitute here the expression of V. So we'll have 1 by C K1 x1 and 1 upon C K2 x2. So this is the nonlinear controls, which is going to control the nonlinear system, equation 1. So this is how we can design control algorithm or control law for the nonlinear system, for this system, using the feedback linearization technique. Now the question is whether the system in our daily life, is it possible to design the feedback lineation based control? So how to tackle this question? So now question is it always possible to obtain feedback linearization technique for the dynamical system? So the answer is if the system is represented in the form of x dot equal to ax plus b and gamma x into u minus alpha x. If we can write any system in this form, if we can write, then we can design feedback linearization based control. So here we can write here, then we can design feedback linearization based control. Okay, so here let us define. So this is our new topic. We can write here. So let us define. This is equation 1, and the control for equation 1, we can write u equal to alpha x plus beta x into v, and where beta x actually gamma inverse. Okay, so here the main thing is, if you have a nonlinear system and if you can define in this form, and in this form the control u will be in this form, and where beta of x, this is basically nothing but the inverse of this function. So if we can write any dynamical system in this form, equation 1, we can design the feedback linearization based control. So now if you substitute, so let us define, we'll take an example for this concept after this method 2. If you substitute equation 2 in equation 1, we have x dot equal to ax plus b gamma x into alpha x plus beta x v minus alpha x. So simply we substitute the expression of u here. Okay, now we will see whether this equation yields to be linear form or not. Let's check. So we can write from this again ax plus, so here I'm writing here somewhere, I'm writing the capital X, small x. You can assume that is the same x. We are actually considering this a vector, you can assume. So here ax, we can write ax plus b. So here this will cancel out. This one will cancel out. So you can write b gamma x, beta x, and b. So what we have defined here, beta x actually gamma inverse x. So you can write from this x plus b beta. So here, if you notice here, our system has been converted to linear form. So our system is yields to be linear form, and you can design the linear controls for this linear system. But to design the linear control for the system, as you know, the A and B, the system should be controllable. So now we can choose, let us choose B equal to minus kx. So this is basically the way we have taken to design control for V. What we have done in actually the modern control. So now let us define, this is equation 4, or this should be equation 3. 3 and 4. Now substituting 4 in 3, we are having x dot equal to a minus bk x. So to design the linear controls for the system, so we have to consider some desired dynamics, and we can compare the augmented matrix characteristic equation, and we can design control. The same approach what you have followed. The condition is we have to consider here a minus bk is Harwich. Harwich means the eigenvalues of the system of the matrix is negative. So here basically all eigenvalues of a minus bk are lies in the left half plane, S plane. Okay, so now we'll go back to the same system what you have considered previously, this example, same example here, and we'll see whether we can apply this method or not. So we'll take the same example here. Okay, so now the system, let's consider the same system, x1 dot equal to x2 and x2 dot equal to minus a sine x1 minus bx2 plus cu. Okay, now in state space form we can write, we should not say state space form, we have to represent that equation in this form, right, in equation 1 form. So this equation we should represent equation 1 form. Now this is equation 5 representing equation 5 in the form of equation 1. We can write x dot equal to, here x dot actually nothing but x1 dot x2 dot. Okay, this x2, and here we can write 0 1 0 0, and we have the variable state variable x2 x1 x2, and we have the B matrix 0 1, and we have C here and we have u minus a by c sine x1. So if you notice here, the system we have, this system 5, we have defined in this form, So here basically we can write, this is basically, we can say, this is A, this is x vector, this is B, this is gamma, this is B, and this is alpha x, right? So now we can write x dot equal to ax plus b gamma x u minus alpha x. We can write. So here, so also we have defined here, if you notice, u is in this form, and where beta is beta of x in this form. So equation 2, from equation 2 we can write, u will be form of, we can write u equal to alpha x plus beta x into v, or we can write alpha x is here basically a by c sine x1, and beta of x actually inverse of alpha x, sorry, gamma x. So here, if you remember, here beta of x actually inverse of gamma x. So we can write 1 upon c and into p. So this is the same form we are getting actually what we have done in the previous example. So here we can write, okay, if v is from, if you apply the linear controls, so it will be minus k1 x1 k2 x2. So we can write a upon c sine x1 minus 1 upon c. We can write, or we can write plus minus k1 x1 k2 x2. So this is our control, nonlinear control. This is, so if you notice here, the same expression what you had before, here also we are getting the same control expression here. So this is how we can design the nonlinear control for the nonlinear system using the feedback linearization based control. And let's stop it here. From in the next lecture, we'll be taking some aircraft examples and how we can design this concept for the aircraft applications. Thank you.